Hi, folks. 3 minutes after the hour, we'd like to get started on time, but 3 minutes late intentionally. Thank you, everybody, for joining. I'm excited for today. We try to do this about twice a year, where we're going to talk about how climate models work. I think the goal of today is to do some basic education. A lot of folks are interacting with climate models more than they ever have, as frameworks like the TCFD ask companies to run climate scenario assessments and then report on this. And then internal teams from finance to operations are trying to figure out what to do with this information, how to quantify it eventually. I think it's just important for everybody to have a baseline of what a climate model is, to talk about it, what's relevant here. And so we're going to talk about all those issues. What I'm going to start with here is just a very quick demo so everyone knows sort of what this looks like at the end of the day. So you should be able to see my screen. I'm showing the Beehive software. What you're able to do inside of Beehive, what our goal is climate models have existed for a long time since insurance started being sold. People have tried to predict what would happen um, uh, to climate, which is slightly longer term from weather, but they're cousins to each other, like we'll talk about today. But what is new because of frameworks like TCFD and regulations like SB 261 is that companies now need to start thinking about these climate models and how that impacts their business. And there's a lot of very complicated math and science in how to develop a climate model, like Ed, who's our chief data officer, is going to talk about a little bit later. And what our goal is to bring as much of that complicated science into business friendly language through very UI friendly software as possible. So, what traditionally you might do if you had to run a climate scenario assessment is send some of your assets, your offices or data centers or warehouses, to a scientist or to some sort of complicated platform, and then wait a little bit as some of these scenarios are run for you. And you might say, what does wildfire risk look like in 30 years? Or what if climate change is really bad or not so bad? And you wait a few months and you get back this data in a spreadsheet, and it's got a lot of like technical information in there that it's hard to act on. What we do inside of Beehive is we actually build these models and try to visualize them right in a software where you can make some decisions and actions off of. So, for example, here's what wildfire risk looks like in North America. And we talk about a scenario. Here's what that might look like in 30 years. And here's what this might look like under SSP5, which we'll talk more about later, but basically, climate change is really bad. And here's what if we're talking about cyclones or what's called hurricanes in North America, or here's if we want to go to Asia and look at hurricanes, but in the present time period. And so all this makes like what I just did in a few clicks here, which is visualize these scenarios and this risk all over the world. And you can do this, for flood risk in Europe or however you want. What you're able to do, what I just did in a couple clicks, is normally a fairly time-consuming project and something that is very difficult to actually visualize and make decisions off of. Now, we'll talk more about this, but one thing that what these laws requires for you to run this assessment, and they don't require you to understand the details of this. And in the United States, an audit is not required of your assessment, even though under Australian regulations, some sort of audit is required under limited assurance. So you may not care about the specific details of how this was created, but your finance team, once they see that you've identified an office at high risk, will want to understand why that is so. And so what we have inside of Beehive is what's called an audit trail, where you're basically able to understand this information and say, hey, why is risk whatever it is? And how did we identify it? And where is this information coming from? So we try to make that as easy as possible to really understand and visualize. So that's a little bit of context. Our goal here is to tell you here's what the risk is to any of your assets anywhere in the world across multiple hazards or risks, so wildfires, floods, whatever, and try to give you tools to understand why the risk is what it is. So you can say, hey, for heat waves, why is it high? Explain to me why heat wave risk is high. Well, we expect this many days of a certain temperature or this number of heat waves. And does it change over time? Well, in 30 years, under the worst climate scenario, you can see all these numbers went way up. And we try to give you that information as easily and accessibly as possible, off of which you can then make decisions, off of which you can report into TCFD, off of which you can begin to quantify this risk in dollar values, understand how much money you might lose and how that changes over time, off of which you might begin to prepare a presentation to your board or to your leadership team to say, hey, I've identified that we have 92 assets in high flood risk right now. Or if we want to focus on our employees, and how they might be impacted by heat waves, and specifically who is often impacted by heat waves. We have folks across multiple states who are impacted by this, or across multiple countries. And so we're trying to give you that information as visually accessibly as possible so you can begin to make some decisions off of it. So with that, I'm going to stop sharing my screen here. I'm going to turn it over to Ed as our chief data officer. He builds a lot of these climate models. He'll spend the next 20 minutes or so kind of walking through the science. Feel free to chime in with questions. The chat is open. The Q&A is open. If something seems like very pertinent and relevant to what Ed is talking about at the moment, I'll chime in so that the context is clear. And otherwise, we'll also save the last 30 or so minutes for additional Q&A. So with that, Ed, you can take it away.
Okay, let's see if I can get this screen up. So is my screen coming through there, Audrey?
Yeah, we see it.
Great. As Audrey said, the mission here is to go through a kind of high-level overview of climate modeling, and I want to talk about a few things. The first is the ecosystem around these climate models. Where do they come from? Who participates? Who develops? I want to talk a little bit about how we use them at Beehive. So how do we get to those scores and assessments that Audrey just mentioned? And then at the end, just look a little bit out on the horizon at what's coming down the pipeline in this space. And this is a slow-moving space, but it's very active right now, and there are a lot of developments that are worth just having a look at. Okay, so climate models, as Audrey mentioned, they've been around for a long time. So they were conceptualized half a century ago or more. And they were initially one-domain physics. And what that means is that they were just a simulation of the atmosphere, just a simulation of the ocean. And like so many fields, additional compute has been a big driver of evolution in this space. So more compute resources have led to an ability to do coupling between the oceans and the atmosphere, to do better models for the transport of water throughout the environment, better radiation models, and also to add more resolution to these models, to be able to describe smaller scale features in the environment and include that in the solution. The mechanics of these models start with a mesh, and it's hard to do better than the Wikipedia graphic for these meshes. So in the upper right here, the gray mesh is a mesh of the atmosphere. There's often an ocean mesh underneath that. And if you look closely at this gray mesh, you'll see the size of these cells decreases a little bit as you get close to the Earth's surface. That's because the atmosphere gets denser, more interesting phenomena is going on there at the surface. And we always want to cluster our data points where interesting behavior is happening. You'll see some of that same thing in the risk scores Audrey just showed. So in asset-rich areas around population centers, we tend to have higher resolution than in the middle of desert areas or far north areas where we don't expect a lot of assets. And that's true of these climate models inherently. After the mesh is made, we need to prescribe forcing conditions for these models. So greenhouse gas emissions are not solved for in these models. They're imposed as a condition, and then that affects radiation absorption in the atmosphere. So there are these externalities that have to be imposed. And once all of that is set up and we solve flow and energy equations, I know some of you are familiar with the Navier-Stokes equations from talking with you. That's the sort of PD that's getting solved here and advanced typically for 100 years. So a typical duration of model results is 100 years, and that happens in 45-minute or an hour time steps, something like this. And this is all happening on data centers and supercomputers. So the scope of these models is all very large. And this, apart from testing, this isn't much run on local compute resources. I'm showing a typical result in the lower right just to give you a sense of the resolution of a temperature field in these models and what the kind of output is. So we can predict very, very fine-grained features. And as an example of that, cyclones tend to get very dramatically underpredicted as occurring events in climate models. But that gives you a scale for what's going on here. Okay, so the modeling ecosystem, the contributors to these things are primarily governments and academia. In the US, a lot of national labs kind of organizations work on this. Jet Propulsion Laboratory, Lawrence Livermore, NCAR, and NOAA, they're big contributors in this space. But this is a very international effort. So Europe has a lot of research centers that contribute, as do Asia and Australia. And this is very, very interdisciplinary. So you can imagine that when you're looking at the evolution of climate, you need atmospheric scientists, ocean scientists, soil scientists, biology if you're looking at how plant life evolves. And beyond the science, there's a big engineering challenge. So when you put together these massive data sets that are produced by running 100 years of the Earth's climate, just getting that out to the public and to researchers is a kind of problem in and of itself. And so the distribution of these results is an engineering challenge. And that's why there are big teams that work on this. That's a nice segue into what CMIP is. So if you look at the climate modeling space, you'll encounter CMIP very quickly, and that stands for Coupled Model Intercomparison Project. And that's really an effort to bring models together. There are many iterations and versions of these models, and it's an effort to bring them all together to assess the models, understand uncertainty, and improve the models. I'm showing a canonical picture of global average temperature evolution in the lower right here, and you can see the uncertainty bounds on those as the color bands. There are a lot of ways to get an uncertainty, but one of them is to run different models and see your spread of results. And that's a driving force behind CMIP. We do get a spread of results in these climate models, and that's why we use ensembles, and that's why we compare them and try to make them all better. CMIP 1 happened around 1995. We're now on the 6th iteration of this. All the data Beehive uses is coming from CMIP 6 simulations. And CMIP 7 is in the works now, and I'll talk more about that in a minute, but that will be the next iteration of this effort. And this CMIP umbrella of data is really the basis of most climate projections. It's really the only game going in town, and it's widely used in industry. A few vocab terms. We don't use these a lot on the Beehive app, but they're worth knowing about when thinking about climate modeling. A GCM is an individual model. So CMIP data tends to be an ensemble of these models, but a GCM is a single model. That traditionally stood for general circulation model, but it also works as global climate model. So you see it written out that way sometimes. And then a more modern vocab term would be Earth system model. That gets at the idea of bringing more and more physics into these models. This is a conference session from the upcoming American Geophysical Union conference where you see that Earth system modeling language being used, and they talk about improving scalability, improving numerics, decreasing resolution, all the things that we just mentioned. And then finally, CMIP, that model intercomparison project language is used for subtopics within climate modeling. So there's something called high-res MIP, which is just assessing these models when they're run at higher resolution, and you try to compare a bunch of variants of that and answer different questions than you can with the baseline models. And that's what's going on when you see these variants of XMIP or YMIP. That's what it means. Adriel showed you some of the SSP scenario parameters in our web app, and so I want to spend a minute talking about what those mean and how we construct those. Scenarios are just the model assumptions that are these externalities that are required by the model and that the model doesn't inherently solve for. And SSP, that parameter selection we have in the web app, stands for Shared Socioeconomic Pathway. That's a CMIP 6 construct, and it refers to macro scale economic related variables like population, GDP, et cetera, assumptions. The greenhouse gas emissions assumptions come more from what's called a representative concentration pathway. That's more of a CMIP 5 construct that was carried over into the current iteration. And that's, again, more of the direct greenhouse gas assumptions. And in CMIP 6, we kind of mash these things together. So SSPs and RCPs are correlated. Some combinations of those make more sense than others. And what we've done in Beehive, and this is pretty standard, is to associate a particular RCP and an SCP, call that a scenario. And so our SSP 1, 3, and 5 scenarios are just associated with particular RCPs and particular greenhouse gas emission lines. And the figure on the right here is from an assessment report that just highlights how different the CO2 trend lines are across these scenarios. So that's kind of what you're parameterizing out when you select this in the app. You're looking at different, probabilistic futures, and that gives you some bounds on what to expect for answers. Okay, so now CMIP at Beehive, how do we use this data? What do we do with it? So a typical risk assessment workflow might start from historical risk rather than going directly to a climate model. And cyclones are a good example of that. I mentioned that cyclones aren't particularly well captured by CMIP models, if at all, because of a lack of resolution at the scale needed to describe convective behavior in those storms. So we could do something like go to a cyclone database and get that historical risk rate at any location. And then we need to understand what are the climate effects on that risk and how will they evolve over the next 100 years or 30 years or whatever our time scale is. And that's easy to do for some risk types like heat stress, where temperature and humidity are quantities that are directly being solved for in these models. That's much harder to do for some risk types like cyclones, where there's a long and nonlinear chain of events that happens to form the storm, and it's dependent on a lot of different variables in the climate simulation, and so it's not a kind of a one-to-one representation, and that gets to be a big challenge, but we deal with this challenge, and wherever we fall in this spectrum, we then project the risk forward in time by going to the CMIP data and asking how do those climate effects evolve, and then how does that affect our risk evolution? And a simple but useful mental model for how to do this is in the upper right here for flooding. So we can break down flood probability into something that stays constant over time, like floodplain information. So, is there a river nearby? What's the local topology? What's the elevation change in my area? That's all very important for flood modeling, but it's not a product of climate model results. Conversely, rainstorm probability or precipitation probability is a product of climate results. That's a function of the scenario we pick and of the time horizon we pick. And that's where the CMIP results influence our risk. And so we combine these two things to get to a flood probability. And that's kind of the risk assessment score. And there's some economic modeling on top of that, but that's the risk assessment, the basis of the risk assessment score that Adriel mentioned. So that's how we use this CMIP data to kind of project a risk type forward in time. Floods are tail events, right? We don't find flooding from the majority of rainfall. We find it only from tail event rainfall, and so we have to look at tail statistics when considering flood risk. And I'm just showing you with this figure in the lower right an example of how we do this. So this is the ratio of extreme rainfall frequency at a projected point, from forward in time from the CMIP models relative to historical extreme rainfall frequencies. And so 1.0 here would be no change over time in the rate of extreme rainfall. And a larger value than one would be, okay, the frequency of these rainfall events is increasing. And you can see for this Africa example, we get not so much change 10 years forward in time. At 30 years forward in time, the model is saying, okay, we're getting a big change in this tail statistic in the center parts of Africa. To just emphasize, at Beehive, we're trying to just kind of stay in lockstep with the consensus gold standard climate modeling. I'm going to show a couple of plots from the last assessment report. So in the top here, you're looking at a global plot of the change in the annual max daily precipitation per degree of global warming. So the scenario is kind of embedded in this plot rather than kind of parameterized out. And if you look at Africa in this top plot, you'll see that same structure of maybe some significant increase in daily precipitation in the Sahara and in the Southeast Africa, less increase around the Mediterranean and Northern Africa and in the tip of Africa. That's the same structure you see in our plot. And then that's not really a tail statistic at the top, but this plot in the middle is a tail statistic. So that's change in extreme precipitation frequency. That's more like what we're showing here. This is a busy plot because it's bar graphs spread around, but if you look at those bar graphs, you'll see the same structure, spatial structure. So more change over time in Western Africa, Central Africa, Sahara, less change in the Med, less change in Southern Africa. And that just helps us to verify that we're using the same data sets and analyses that are going on at the CMIP consortium level and the conclusions from the international scientific community there. Okay, I'm gonna talk about.
Ed, I want to pause.
Yeah.
Sorry, Ed, there are a couple of questions here,
Oh,
one of
great,
which
great.
is
Yeah.
timely. So Michael's asking, is it fair to consider that the models at a global scale, which are the strongest, are late century, and they're more dirty near term because of natural variability, will make it difficult to make predictions in the short term. So how does confidence change over time, I suppose?
Yeah, very good question. Very interesting question. So, um, I think maybe I would frame that question as signal to noise ratio. And um, I don't know that I have an immediate comment on how whether that signal to noise ratio changes significantly over time. I would say um, in the near term, we have the benefit of being able to extrapolate out the current trends and just check the climate modeling results against them. In the longer term, that's harder to do. So that's maybe where you could say, well, if there's certainly noise in both cases, but you can filter for that noise a little bit better in the near term by checking against current climate trends. And then I would also say, because all of these models get parameterized by scenario, and because in reality we're only on one scenario that is not an exact representation of any of the scenarios in the climate models, right? So the reality is somewhere between all of these. You have to account for the noise just of the scenario prescription process. So as time goes on, this is the scenarios are always collapsing to reality. And the question is, like, based on where we are now, which scenario is most representative of where we'll be? And again, in the shorter term, you can kind of do that. So there's noise from, maybe we're between SSP1 and SSP3 right now, so there's a lot of noise from SSP5 at 1 year out that isn't really valid signal. But as you project out farther in time, it becomes less clear exactly which of these scenarios will be between, and the noise increases. That's, I think, not an exact answer to your question, but maybe gives you a sense of how I think about that signal to noise ratio in assessing scenario inputs and near-term duration versus long-term duration.
Yeah, I'd also say, and it's kind of tied to Asheen's question, which I'll read aloud in a second, but these are not predictions. Like, I don't think you should be treated as, oh yeah, we're definitely moving in the SSP5 direction. This is what's going to happen. This is an accurate crystal ball of what's going to happen. I think this should be treated as like stressors. Like the banking industry does this a lot. Like, what if all of a sudden there's a crash? How do we have enough money? Like, we're not saying there's going to be a crash, but what if there was a crash? Do we have enough money? I think this should be treated as we tie to what a business is doing with this information in a similar way. Like, what if we did? And my comment here will be, I think there's a lot of stuff in the scientific world that is not necessarily relevant to the business world. And we talk about this all the time. The year 2100 is a very interesting year in the science world, and it is a relatively irrelevant year in the business community. And so the fact that the business world is sometimes being forced to look out, or forced, I don't know, encouraged or whatever, to look out 30, 50, or 70 years is just kind of square pegging in a round hole. The reason I bring that up is because the Sheen's question is there a consensus or best practice among corporates for which SSP to use in our TCFD reports? Meaning, if you're a company and you are reporting on the results of your risk assessment or what you're planning for around this business, which SSP should you use? What we see most common is people say, I'd say among our customers, because you did this across three SSPs, is we did this across three SSPs and we found more stressors, obviously, around SSP5 than around SSP1, but we were thinking about all those scenarios. So from a reporting perspective, like, you're thinking about all the scenarios. You're saying, here's where my risk would lie under SSP5 in the longest term, which will always be the worst, is probably not the perfect word, but the most detrimental or most challenging scenario. So I think you can talk about that. Now, how your business prepares for that could be a little bit different. Um, I would recommend thinking about SSP5 because that is that worst case scenario, and whether or not we will get there. If you're prepared for that, you'll do well under other SSPs. But from a reporting purpose, most commonly companies are saying we ran this across multiple scenarios, multiple SSPs, and multiple time horizons. So at Beehive, it's 1 year, 10 years, and 30 years. Different platforms, different companies go out all the way through 2100. So it depends on what you do. Anything did I eat my tongue there, Ed, or anything to add?
That was fabulous. Very, very well said. I will add on to it and say it's very uncommon in climate modeling literature to look 1 year out, right? Because the rate of change is very slow over 1 year. And so there's kind of noise in the sense that that's not commonly viewed as signal in the climate modeling community. It's much more common in the climate modeling community to do something like break your 100 years up into two periods. One is 60 years to 100 years out, and the other, the baseline period, is maybe like 0 to 40 years out or something like this. But as Adriel was just alluding to, that's not very helpful for most business timescales. So as Adriel mentioned, we think a lot about how to make these timescales relevant, but also tied to the underlying purpose of the climate models, and try to fall somewhere that kind of has a hold on both ends of that spectrum. Yeah.
Yeah. Brendan asked a good question here, which could be read in one of two ways. And I think it could be interesting to answer both versions of it. And if you want to clarify which version you meant, go ahead. But Brendan asked, how might the change in US government funding affect these climate modules? I think there's two ways to read that question. Question one is, if the US is not funding scientific research, like from NOAA or gathering data from via something like FEMA, how does this change our ability to build a model? That's one version of the question. I'm going to let Ed answer that. And then the second version is, how does US government funding towards decarbonization or clean energy adjust which scenario we go to? Obviously, the US and China and India as big players, the more you decarbonize, the less likely that an SSP5 scenario happens. And so if the US and other large economies don't fund decarbonization, we are probably more likely to head towards I think SSP5, they even have these like phrases, I forget exactly what they're called, but SSP1 is like the orderly pathway. Like governments are really implementing a lot of policy and we're moving towards clean energy. And then there's like a disorderly transition, which is SSP3, and SSP5 is some sort of chaos. And that's because governments are not investing. So that'd be how does a lack of funding and decarbonization impact the modules? But Ed, if the US government is not funding NOAA and FEMA and similar agencies or similar research labs, how does that impact our ability to continue to do this modeling?
So that has an impact. It's non-zero, but it's not dramatic either. So, for example, a lot of the CMIP6 data sets, which are already produced and out there in the public, are hosted on non-governmental locations. So Google, for example, hosts a lot of CMIP data on some of their drives and makes that publicly accessible. So there are a lot of data sources in this space that won't be impacted by a change in how some of these labs that are producing them, that are working on the models, operate over the next 6 months. It's very theoretically possible that affected labor at some of these labs could affect the CMIP7 timescale from U.S. contributors. But again, this is a very global effort. It's a consortium of researchers around the world, and so a big bulk or big chunk of those research activities won't be affected. There's a non-zero impact, but I don't think there's much risk that the project kind of gets sidelined or dramatically affected, I guess is how I'd say it.
Cool. Great questions, team. Keep them coming. Ed, go ahead.
Great. Yeah, I'm just going to push on that use of CMIP data for one more slide with a heat risk application. So as I mentioned, heat stress is one of the easier things to extract from the climate models because the variables are all right there. And what we do for this risk type is to extract temperature and humidity from usually 20 or so of these simulation results per scenario of interest. And then we aggregate all of that data on one mesh. So I mentioned that the mesh is a fundamental part of the simulation. When we're talking about a CMIP ensemble with 30 or 50 different models from around the world, they've all used different meshes. So just dealing with the infrastructure to get that onto the same mesh is a little bit of work. And then we build risk-related stats. So just like with flooding, we're interested in tail events of precipitation. Here, we're not interested in whether it's 20 degrees or 30 degrees in Greenland. That's not a big driver for heat stress. We're interested in things like what's the 90th percentile of the daily max temperature observed at this location, or what's the 98th percentile of daily max wet bulb temperature, where we account for humidity effects. And we build a number of those stats. You can see a couple on the right here for North America, and then we composite those. So we kind of weight each one and bring them into a single number. And then we score based on that composite heat stress. And we have to make some scoring choices that are non-trivial and that I think are not it's not a choice where there's a right and a wrong decision. And I say that because there are a lot of academic papers that have proposed a lot of different heat stress metrics, and the community is not coalesced around only using one. There are a lot of these. They're all meaningful, and they have some information to provide. And so we have to make a choice about which of those to use, how to make this composite. For example, how to define heat waves, right? There are a lot of different ways you can find when a heat wave occurs. Is that relative to the baseline temperature for the area? Is it relative to an absolute temperature? How many days do you need the heat wave to go on before you call it a heat wave? And different locations around the U.S. at the kind of weather monitoring level do this very differently. But nevertheless, we have to make a choice. So we try to make a reasonable choice that accounts for most use cases, and then put that composite together and then score. And that's what gets us to the risk scores that Adriel mentioned in the web app. And when you look at that audit column, what you're seeing are some of these individual risk-related stats that we're calculating from the CMIP data and then bringing along with the final score so that you can get a sense of where things come from. So that's the idea here of the flow from CMIP data into the risk score. And I'm just going to spend a slide at the end here before we go to more questions on what's on the horizon in this space. So climate modeling is very slow moving, but CMIP 7 is coming down the pipeline. Simulations are probably running right now. It's not always clear exactly what the status is, but data is expected soon enough that they're very much in the works. And I think we could have early data release as soon as before the end of the year or next year, but the bulk of the data will still be a little ways out. And that's a very active topic. You know, what do we do with the CMIP 7 data? What are the thresholds for getting your data included? What are the evaluation metrics? That's a topic for academic conferences currently. And these simulations in CMIP 7 will have more resolution. So maybe we'll get a little bit closer to simulating some of those cyclone events in these models. And they'll have more physics models be a part of the simulation environment. Beehive will be an adopter of this. So when the CMIP 7 data reaches critical mass and comes online, we'll use that. We'll plug that into our risk analyses flows, but we won't be running these models or contributing to their development. And until that time, we're going to use the current standard, which is CMIP 6. And then finally, I want to talk about AI in climate. It's fun and it's very, very timely right now with all of the development going on in the climate modeling
And
community.
sorry, just a question about CMIP 7.
Yeah.
Um, what should people expect might change? Like what
Yeah,
what
great
is
question.
what would be relevant about maybe what's the difference between 5 and 6? What could change? And then we actually haven't talked about this, so I'm curious what you're going to say here. Like what would change about how a business deals with these findings? Is it like, sometimes in carbon emissions, new emissions factors come out, and all of a sudden my water bottle that used to be 10 grams of carbon is 15, and everyone's like, what? Okay, I guess it's 15 now. Like what is expected to change in CMIP 7, and then how might that impact what a business does with that information?
Yeah, I would say in general, you're on pretty safe ground if you expect very little to change in the results in a way that would affect your risk assessment for your company. And the reason is that um, first of all, a lot of the risk assessments we're doing are in the near term, and that's again on a trend line that we can extrapolate a little bit, and those trend lines don't change rapidly. And so if you're looking at it in the near term, there's just in the models that we're currently running are doing a reasonable job, which they kind of are. Then there's no reason to think something in CMIP 7 will dramatically shift those curves one way or the other. There will very surely be small differences, and the longer of a time scale you look at, the more those differences would widen. As you'd expect, if there's a gap, it's going to grow over time. But for the most part, I wouldn't expect significant differences that will affect your reporting or risk assessment, because the fundamental engines of these models are going to remain the same. It's just going to be iterative improvement rather than a seismic shift in what they describe.
Cool. Thanks.
Yeah, and then on the AI topic, all of the technology that we're using in LLMs right now turns out to be applicable to these climate models in a kind of interesting way. And at some of the recent business conferences in this space, we've heard about how AI can drive increased energy usage. It requires more data centers. The climate space is interesting because a lot of the AI application here is actually lowering energy use in these climate models. That's, of course, a tiny sliver of the overall pie, but it's actually an area where the AI operations run more cheaply on a per energy basis than some of the traditional PDE models. And big techs and startups are working on pulling this technology into the climate model evolution solution. And I want to just get at that with what I show on the right here, which is a couple of images from this very famous paper in computer vision that introduced AlexNet. This was a while ago now, but it was one of the original papers that was highlighting which patterns a neural net could learn from an image. And you see those kinds of micro patterns at the top here. There may be light and dark patterns of a diagonal line or horizontal line or color banding or anything that's kind of a fundamental geometric shape. It aggregates all those micro patterns into bigger patterns, and that's what it's using to detect kind of known semantic objects like a mite or a container ship in images. And it turns out that that pattern recognition technology that's so endemic in computer vision right now can also be applied to some of the fundamental variables in climate modeling. That's pressure, temperature, velocity, those physical quantities that we've traditionally been solving for with PDEs. And so, that application is done through transformers and graph neural networks rather than PDEs. So there are a lot of efforts to use hybrid models now where you run some kind of traditional partial differential equation solver at a coarser resolution, but then you augment it with an AI application, kind of like an image generation tool or an object detection tool that fills in the finer resolution features in the model. And so at the top here, I'm showing a result in the paper from Google's neural GCM model, which is just that. It's a combination of a PDE solver and some AI technology to do data fill in. And NVIDIA's core diff does the same thing in a little bit different way. You're looking at plots at the bottom here of simulated radar reflectivity. So what a radar would look at if it was considering the simulation data for a cyclone event at the top and then for some storm events in the lower two pictures. And the AI can do a pretty reasonable job of filling in this information and projecting it at a much lower energy cost than it would take to run the PDE model at that same resolution. So that's a very interesting development that we'll be seeing more of in the next few years. I don't know if these AI capabilities will be a part of CMIP 7 or not, maybe a little bit, maybe not. But down the road, I think they're going to have more of a place rather than less of a place in the climate modeling data. And we'll just be in watching that and using it as it comes along. And that's where I want to stop. Thank you for the attention and the questions. And I want to direct everybody to our documentation. If you haven't looked at it, if you want to get more of a sense of how we do some of these individual risk models, there's a little description there. And very happy to hear feedback on any of these topics. We want to kind of know what's helpful and what's useful to hear more about, and what's data that's kind of noise and not helpful, and that helps guide what we do. So thank you very much.
Awesome. Thank you, Ed. Um, I'm trying to figure out if there's a question, Michael's question here, or if it was just a statement about granularity. I'm not sure if there's a question of that, but I'm going to ask a question about granularity. I can rephrase that if you could like. We talk a lot about trade-offs, meaning climate science, like a lot of science, is one of those disciplines that could be a black hole. You could have, I mean, you do have thousands of scientists working on this for decades with all the dollars in the world, and there's no end in sight. That's the kind of the point. You always get a little better. We can't afford that as a business, and also our customers don't necessarily need that to make business useful decisions. Can you talk a little bit about some of the trade-offs that you make intentionally around granularity, for example, or resolution, or how many data sets to incorporate, and maybe give a specific example of something you decided not to do intentionally because we thought at the service that we're trying to offer, the price we're trying to offer for, we had what we needed.
Yeah, you bet. A great um, topic to get into that is building by building characteristics. So if you want to maybe do flood insurance on a building and you're very interested in which construction type it used or when it was built, and that's going to affect your flood insurance policy, then those are details that you need to know about to argue with the insurer about what the risk assessment should be. To get that data, you need building by building, and to do a global scoring assessment, you need building by building data for literally every building in the world. And that's, of course, very expensive data to get. You can start doing things like making assumptions regionally or city by city, but it's not hard to imagine that if you take a city like New York and you've got some housing or older industrial buildings next to a skyscraper, you're immediately going to get into errors with your building assumptions. That there are cases where you can do that. There are great examples for doing that, and there's value you get by doing that. As you talked about, there's a trade-off there with, is the effort and the cost of doing that building by building assessment worth it for your application? And our view is that for a lot of companies and a lot of risk assessments, that level of granularity and potentially, that input to a discussion with an insurer is not going to be value add for what you need to assess that risk within your company, where you need to know about your buildings, but nothing else, and you've got some of that data handy, and also to report on that risk, right? So maybe another way of saying it is you can dial in your risk assessment or your economic loss assessment more and more as you get more and more data about your building, as you kind of make the lens you're using to look at your risk finer and finer. But it costs more and more to do that. And so there's a sweet spot in there where your interest in understanding the risk matches the cost you're willing to pay for understanding that risk. And we've tried to hit that sweet spot for a wide range of companies. We won't do it perfectly for everyone, but we try to be kind of generally applicable at a reasonable cost of data assimilation and analysis, without going to that full bore building by building kind of assessment around the globe. So does that kind of get at what you're
Yeah.
there, Andrew? Yeah.
No, I think that's a good example. We talk about that a lot, and that what that means is like it was a good fit for Beehive. Honestly, if you're a massive real estate owner who pays a lot of money in insurance and needs really good building by building specific risk scores, we're probably not a good fit. They're just not going to be there. But if you need something global and reasonable and auditable and transparent, we try to do a good job there. Sheen asked a question. Michael, you asked a question. We're not insurance experts, so I don't want to speak to something we're not totally qualified to speak on. That said, we are going to try to do a webinar soon specifically about insurance. So stay on the newsletter. We'll answer a lot of those good questions. Sheen asked the question, with the combining of climate models, do we expect climate modeling to be more settled these days and change less? Or are we still in a period of flux while the science is developed? I guess how much debate is there over what you're using and how we're doing this?
I think there are areas of debate. I think there are a lot of big muscle movements that are somewhat settled. They're just not active research threads in the climate modeling community. Is temperature change, for example, it matters which SSP scenario you're on, but I don't think there's a lot of discussion within the modeling community around are we way off base with the answers here? Are there things that we're going to change that are going to dramatically affect global average temperature curves? I think that's not that active of a research discussion, and I think not much will change between CMIP 6 and CMIP 7 on that point. There are subtopics though where that's a very active discussion, and I'm going to go back to cyclone modeling. So again, currently. Cyclones are not captured in these models because there's not enough resolution. So what people do to project cyclones out into the future is kind of a diverse set of of approaches. You could run a regional model. So you run just the North Atlantic in a much higher resolution simulation, and the boundary conditions of that model are populated by the results of a global CMIP model. And then when you add in that resolution, you try to understand how cyclones will evolve. Other people do things like statistical analysis to extrapolate out the dependency of cyclone occurrence on a climate variable like temperature or amount of water content in the atmosphere, and then they use that to project out cyclone frequency changes. And right now, you see pretty dramatically different projections of cyclone frequencies across different papers. Our approach to that at Beehive, going back to the trade-off discussion, is to kind of just take an ensemble of all those results. We don't want to be a referee in that discussion. We just want to take an ensemble of the current best thinking in the research community and use that. But there are very diverse views on that, and so that's a subtopic where more resolution might lead to predictions in CMIP 7 or maybe CMIP 8 that really cause a consensus to form around a question that's open right now. But there's a few of those questions. There are also a few questions that are pretty settled and that are not so interesting and not expected to change between CMIP iterations.
Yeah, one of the things that we talk about a lot, and when I first called Ed with this idea for Beehive, I was like, well, wouldn't it be nice if I don't know if you could be right about what's going to happen in the year 2050. That feels like a crazy thing to promise a customer. We are correct. Our models are correct. So that's is not our goal to say we are correct about what's going to happen in 2050. I think our goal is we always talk about auditability and transparency. Transparency shows up in things like this in our documentation, and we try to every way in which we can say, here's how we do this, and people can debate it and ask questions about it. We want to do that. That is the goal. And auditability is a bit of that audit trail that I showed you of like what we want to provide our customers who are corporates more than they are insurance companies or governments or banks, but corporates is the ability to have confidence and disclosure. So where did you come up with this number? Well, why do you think the number is what it is? Is there some good science backing it up? I think that is helpful. And anything to add about how you like we talk about auditability and transparency all the time, but how that shows up in your work?
Yeah, I think you said it very well. I don't have a lot to add to that other than that exactly as you said, um, we are not writing a new model to be or running a new model to be more correct than the existing models. We are trying to use the consensus from the state-of-the-art modeling community to inform these risk analyses with the complete understanding that this is a probabilistic exercise. We can kind of look at bounds on where things will go, but we can't predict the future. We can't predict exactly where in these bounds will be, and there's some inherent uncertainty, and we're not trying to resolve that uncertainty. We're trying to give everybody a tool set to look at it and use it, right? All models are wrong, some are useful. We want this to be useful rather than not wrong. Yeah. Yeah.
Perfect. Yeah. Um, I have one final question because I think it's just kind of relevant to how customers actually interpret this data. I'm going to share my screen here really quickly. Um, but in our app, we have risk scores on a scale of 1 to 7.
Hmm.
And you can see low is 1 through 3, medium is 4 through 5, 6 through 7 is high. What should a customer think when they see heat waves are a 6 out of 7 or floods are a 5 out of 7? Should I be thinking I should only care about heat waves and not floods? Should I be thinking wildfires will never ever happen in this area because they are a 1? Like, talk a little bit about this 1 through 7 score and how that translates to low, medium, and high, and what a customer should think when they see these numbers for one of their assets.
You bet. The first key point about the 1 through scoring 7 system is that its goal is to give users a quick look at risk. So if you do not want to dive deep, but you want to get a quick assessment of what's going on with different risk types, we want to give you that info. And because of that, the goal to make this quick and interpretable, we have to condense a lot of information into a single number. What's going on with the 1 through 7 scoring thresholds is that we're looking at locations around the globe and doing a kind of relative ranking of risk. So, for example, for heat, if you're a 6 or a 7, you're going to be in the top 20% of locations around the globe that are subject to heat stress, according to the composite metric that I talked about. Some combination of humidity effects, max temperature effects, heat waves, and that won't tell you exactly how many heat waves you're going to get, but it tells you this location relative to all other locations around the globe is a high risk. So that 1 through 7 scoring system it's fundamentally a relative scoring system rather than an absolute scoring system. If you're interested in diving deeper and understanding more about quantitative physical metrics associated with those numbers, the audit column or the audit sidebar that Adriel showed is a great way to do that. So that's where you can go from, okay, this is a high risk area compared to locations around the globe, to, well, this is why it's high risk. Here's how many heat waves we expect this to get. Here's how many days, here's the kind of max wet bulb temperature that we expect to see at this location over some sustained period of time. And if you're interested in doing a quantitative analysis on top of the risk scores, you want to go to that audit data to get the inputs to that relative global ranking system. So again, the idea is the 1 through 7 system gives you a quick look at how risky this location is relative to locations around the globe, or what the risk probability is. And then to go deeper than that, you need more info. And that's where we try to expose the info in the audit trail.
Perfect. Ed, thank you very much. Thank you all for joining. We do this every single Thursday pretty much when there's no holiday. The next three we have coming up next Thursday. I did a talk at Columbia University a couple weeks ago, so folks seem to like it. I'm just repeating that. We'll see if that's fun or not. It's an experiment. The week after that, on November 20th, I'm talking to somebody I love, Sophia Gluck, who's the head of sustainability at Okta, kind of talking about their sustainability strategy. And then the first Thursday of December will be our last webinar of the year. It's a Beehive product deep dive where we go through the entire product as it is today, what is on the near-term roadmap, and what is part of the vision. Thank you all very much for joining. My email is adriel@beehiveclimate.com. Ed's is edward@beehiveclimate.com. Reach out with any questions. Ed, thank you very much, and I'll talk to
Thanks.
you all soon.